What we're going to do today is learn about the third circular function, the tangent function. So that's 6j. So today you're going to learn how to sketch this function and also how to solve equations using tan. What you need to be able to do is identify the key points of the tangent function, including its asymptotes, in order to be able to sketch these from its rule, and also to be able to find the x-intercepts. So let's talk about the tan function. What does it look like? So the best way to be able to do it is to substitute in various x values to be able to find out what that is. So if x is equal to 0, if our angle is equal to 0, then we are over here. How do we find tan? Tan is simply equal to sine over cos. So here, my x value is, well, actually it's the other way around, isn't it? 1 and 0. So the tan value for that, for 0, for our angle is 0, is equal to the y value, which would be 0, over the x value, which would be 1. And that's this scenario here. So our y value is going to be 0 divided by 1, and 0 divided by 1 is just 0. So when my angle is 0, my y value is likewise going to be 0. If we look at moving around the unit circle, so let's look at pi on 2. So my x value now is 0 and my y value is 1. So now we're looking at this situation. So y over x, sine over cos. So we're going to have 1 divided by 0, and in that case, that will be undefined. So at this value of pi on 2, we are undefined, which means that that will be an asymptote. We can continue moving around the unit circle. So at pi, our x value is -1, our y value is 0. So 0 divided by -1 is going to again be 0. So that means that that is another intercept. So what is this telling us? It's telling us that every time we have pi on 2, 3 pi on 2, anything on 2 will always end up undefined because the x value is 0. So anything divided by 0 is undefined. And then anything that is at 0, pi, 2 pi, or -pi will be an intercept because that will divide out to be 0. Now you can substitute in a few other values as well to be able to find out what the shape of tan is going to look like. We don't just hop around from point to point. I'm just going to move my asymptote over a little bit because it doesn't really seem to be even. There we go, that's a bit better. But what you'll find out is that when you do substitute in your values, your tan graph will end up looking like this. So we'll approach the asymptotes as such. Of course, the asymptotes will usually be drawn a lot straighter and better than the way that I have. But this here is the graph of y equals tan x. Let me take you to a better sketched graph. So this is what it'll end up looking like, and that is through substituting in these certain values here. So let's talk about the graph of y equals tan x. What you'll notice, unlike sine and cos, is that we have this graph repeating not every 2 pi, but rather every 1 pi. So the difference between negative pi on 2 and pi on 2 is a pi, and then same thing between pi on 2 and 3 pi on 2 is 1 pi. So the graph repeats itself. Why is that the case? Well, hopefully you remember that tan is positive in quadrants 1 and in quadrants 3. So what that means is that the value actually just repeats every pi. That's different to what cos and sine do. So sine is in quadrants 1 and 2, and cos is in quadrants 1 and 4. So it doesn't look like it's repeating every pi, which is what is happening here. So that's the first point there. And the next one is that the range of tan is r. So what happens is our values approach the asymptotes. They're never going to touch them, but they will approach them, and so they will continue on forever. We do have asymptotic equations that is equal to this. X is equal to plus minus pi on 2. Of course, that is dependent on if we have any transformations that occur. So we'll talk about those transformations in a moment. And the x-axis intercepts occur for x is equal to, and that should be at 0, pi, 2 pi, and so on. I'm not sure why it's been cut off there. But anything that is a multiple of pi is when we will have our x-intercepts, unless, of course, we have any transformations. So let's talk about one of our transformations, which is if my dilation is changed, so we have a different period. So the period of the function, as you recall, it repeats every pi. So if I have n, it will become pi on n. Unlike, again, sine and cos, their period is 2 pi, so that's why the rule is 2 pi on n. The range remains the same. However, the asymptotes are no longer pi on 2, it's now pi on 2n, because we need to divide by that dilation factor. The formula for the asymptotes has changed as well. Now what you'll notice is that on your paper, it'll say 2n plus 1, but we've already got an n, so I would like you to write k instead. So k in this case is going to be the cycle number, and n is, of course, our dilation factor. So just so that you don't get confused, we're going to call it k just to make it a little bit easier. So if you want the first asymptote, we can substitute in 1, second asymptote 2, and so on. And then the x-intercepts, before it was k pi, or rather it was at pi, 2 pi, and so on. So we're going to have k to represent the cycle number again, and then divided by n, which is once again our dilation factor. So now that we have all of this information, we're going to go ahead and start sketching. So this says, sketch the graph of the following, state all axis intercepts. So what we can do here, because there's no translation up, down, left, or right, it's actually quite easy to be able to find it given our original graph. So let's talk about our original graph. One thing actually I've just noticed is it hasn't really given us a domain. So I'll just say that our domain is between negative pi and pi. Now, because of this 2, if you remember, that means I'm going to go for twice the number of cycles for every 2 pi that I have. Another easy way to sort of think about where should I find the values between is if you multiply it by 2, it'll tell you what initial values you need to find. And then when I'm going to go ahead and divide everything by 2 to get x by itself, when I divide by 2, I get back to my original domain. So that's just a side note to help you out if you need. We'll also notice that there is a reflection. So our graph is going to now look like this. It's been flipped around. And the 3 in this case, it's not the amplitude. It doesn't really do anything. It's just a dilation factor, but it doesn't do much in this case. So how can I go ahead and sketch this? Well, I think the easiest way to do it is using all of our original values of a tan function and then applying the transformations that we have. And really the only transformation that I have here is the dilation by a factor of a half from the y-axis, so dividing everything by 2. So if I were to think about my normal tan graph between negative 2 pi and 2 pi, what graphs or what values would I have? So I would have an intercept at 2 pi. I would then have an asymptote at negative 3 pi on 2, then an intercept again at negative pi, and then an asymptote at negative pi on 2, and then an intercept at 0. And hopefully you can see where I'm going with this. I'm just trying to work out what would my normal values be if I didn't have any kind of dilation. Now, of course, this looks like it's outside of my original domain, but remember, this is what my original values are equal to. In this case, my angle is 2x. It's not necessarily that x equals, but it's 2x for each of these values. So now what do? I'm going to just divide everything by 2 to give me the new graph. So the new graph will have intercepts at everything here that has been divided by 2. Intercepts and asymptotes in this case. Oops, there's no reason there's a 3 there. There we go. Okay, so everything has been divided. Of course, 2 pi and 2 would just be equal to pi. I should have just divided that straight away, like I did with the first one, but 2 pi divided by 2 is just 1 pi. So now we can see I've got intercepts here, and I have asymptotes here, and I can see my not translated, but my transformed value because of dividing everything by 2. That's pretty much all the information that I need. I can now go ahead and sketch this graph. So I can put in all of my values. Trying to keep as best as you can to the scale. And now I'll put in my intercepts. And my asymptotes. I'll just use another color just to make it a little bit easier. All right, and now I can go ahead and sketch my graph, remembering that we've got a reflection here. So I'll start with the 0. That's always the easiest. So we can go like this and then down. And then each of these is going to have the same thing happen to them. Now, why did I leave the ends to the end, well, what's going to happen is it's going to be cut off. So you can see that there is not a full cycle there, and it looks like it continues like that on the other side. So that is what my graph is going to look like. Next one, part B. Now we need to sketch the graph of y equals 10 to tan x minus pi on 3. So in this case, we don't have any changes to our period, which is very helpful. But what I can notice is that I do have a translation. So basically what's happened is I've added pi on 3 to every single one of my points. Now, once again, because I don't have a vertical translation, I don't even need to go ahead and find the x-intercepts through solutions. I can just use the same technique I used previously, so finding my key points and then adding pi on 3 to them to be able to give me all of my new points. And I think that that's the easiest way to do it. So let's do that. First step, we're going to write out our key points as we had before. Once again, there's no domain, there is a domain that has been given here. It's from pi on 6 to 13 pi on 6. Originally, what you might notice is that, the distance between it looks very similar to between 0 and 2 pi, but we've just added pi on 6 to it. So initially, all of my values need to exist between 0 and 2 pi, and then we can see that it's been translated over, or the domain has been translated over as well. So let's find all of our key values. One thing that I want you to keep in mind, just as a little tip, is that when I have an original graph that might look like this, when I actually translate it over, new values that was here before might now appear as part of my domain. So what I like to do is always find a value or two from that was outside of my domain that might be dragged into my new domain, that might be dragged into being part of the picture. So that means that even though I know my initial intercept would be at 0, I want to start one step beforehand. So I know that one step beforehand, I've got an asymptote at negative pi on 2, then 0, then I've got an asymptote at pi on 2, intercept at pi, asymptote 3 pi on 2, and intercept at 2 pi. Now what's happened to each of these according to the transformation? Well, all I've done is I've added pi on 3 to every single one of these points. So we can go ahead and do that. Now, you just need to remember that the denominators need to be the same. So you will just multiply each of these by 3. So if I want this to be on 6, this would be negative 3 pi on 6 plus, and then to get this to 6, that'll be 2 pi. So negative 3 pi on 6 plus 2 pi on 6 will be negative pi on 6. Now in this case, it's actually not appeared to be a part of my domain. It might have though, which is why I put it in just in case, but in this case it hadn't translated in. All right, 0 plus pi on 3 is just pi on 3. Pi on 2 plus pi on 3 is going to be 5 pi on 6. Then we will have 4 pi on 3. Then we will have, that I'm just doing 3 times 3 in my head. So to make that on 6, that'll be 9 plus, and then times 2 here. So 9 plus 2, that's 11 pi on 6. And for the last one here, we will have, this one I can just multiply by 3. So that'll be 6 pi on 3 plus 1 pi on 3 will be 7 pi on 3. So now I can see that all of my values have been translated. I just need to make sure that they're all within my domain. As we spoke about, this value will not be a part of my domain because it's below pi on 6. The question is 7 pi on 3 below my domain? Well, I just need to know what it is in terms of on 6. So if I were to make this on 6, I will say that that's 14 pi on 6, which is outside. So that also will no longer be in my domain. Other than that, I now have all of my key values. So these are my intercepts, and these will be my asymptotes. And now what I can do is go ahead and sketch this. I might use a different color. Okay, so our new intercept that used to be at 0 is now a pi on 3. Then I will have an asymptote. Then I will have another intercept, and then one more asymptote. And I won't have anything else. My next intercept is just outside the domain. There's no reflections or anything, so my graph will continue on like this. Now, the next question here is, where does my graph stop? So I know I have to do this, and I know it's not going to reach the intercept. So at what point does it stop? And same thing here, it's where is pi on 6? Where does my graph stop? So before I finish this graph off, I need to go ahead and find my endpoints. So I'm going to sub in my endpoints. When x is pi on 6, that will mean that my y value will be as I find now. So pi on 6 minus pi on 3 is going to be negative pi on 6. And if you remember our rules, negative tan of negative theta is equal to negative tan of theta. So that'll be negative 2 tan pi on 6. And then we need to remember our exact value. So that will be 1 on root 3. When I multiply that by 2, that'll be negative 2 on root 3. So I know it's a negative value. That'll be pi on 6 and negative 2 on root 3. And you can rationalize that if you like, but I'll just leave it as it is. Now, very often, the endpoint on the other side will be exactly the same, because in this case, it's 2 whole cycles away. So between 0 and 2 pi, as I said, and all that's happened is we've added pi on 6 to our cycle. So because it is exactly 2 cycles away, I can safely assume it'll be the same endpoint on that side. If you're not too certain, then it's worth just substituting in that value to make sure. We have one last example now, no more sketching, which is very nice. But what we want to do in this case is solve the equation 3 tan 2x is equal to root 3. Now, this is really important to be able to do for graphs where there is a vertical translation. So what this actual graph would be, if we were to sketch it, and we might give it a quick sketch at the end, would look like this. So I would essentially take the root 3 to the other side. So what's happened is there has been a downward translation of root 3. And what I'm trying to do when I make y equal to 0 is find the intercept. So that's why I need to solve this equation. We're going to solve it just like we solve all of our other equations. So we'll have 3 tan 2x is equal to root 3. I'm going to take the 3 over. Now, root 3 on 3, that's the same as 1 on root 3, but it's rationalized. So when we think of our base angle, or our angle of tan, that will give us root 3 on 3, that's going to be pi on 6. So step 1, we need to find our base angle. In this case, theta is going to be pi on 6. Then I need to think about, well, this in this case is a positive value. Where is tan positive? It's positive in quadrant 1 and in quadrant 3. So the rules for that are theta and pi plus theta. So you'll notice that it's exactly 1 pi away because I'm just adding pi to it. So given this, we're going to have our angle, which in this case is 2x, is equal to, and we will substitute in our values now. So theta is pi on 6, and then that will be 7 pi on 6. And remembering that what we need to do is, because there's a 2 here, and it's between 0 and 2 pi, that means I need to go for 2 cycles. Or another way to think of it is if I multiply it by that value, I need to find all the values between 0 to 4 pi, because in a moment when I divide by 2, I'll go back to 0 to 2 pi. Okay, so how do I get to the next ones? Well, I'm just going to add 2 pi to each of these values here. So pi on 6 plus 2 pi is going to be 13 pi on 6. And then 7 pi on 6 plus 2 pi, so that'll be 7 plus 12. That will be 19 pi on 6. And finally, to get x by itself, I'm just going to divide everything by 2. And what you'll notice is that all of these are now within my domain. So what have I actually found in this case? Well, I've found my x-intercepts. And if I wanted to give this a very quick sketch, it's very straightforward now because I've got those x-intercepts. Of course, what you'd normally need to then do is find the asymptotes, which you can use the equations or you can use another technique, which I'll show you in a moment. I love my fake axes. I think it's so much easier to draw. So if I know the whole graph has dropped by negative root 3, I found that out by taking it over to that side, then I can put in all of my points and start drawing my normal tan graph. So normally my tan graph starts at 0, so it'll start here, and then there will be an asymptote. That will be pi on 12. Then I will have this. That will be 7 pi on 12. I'll have another asymptote. And again, I don't know if this is going to fit. This will be 13 pi on 12. Sorry, I know you can't do this in your book, but I need a bit more space. And then we'll have our last cycle. That'll be 19 pi on 12. And I know that that's going to end at 2 pi. So we need to see whether the asymptote will be able to lie in between there or not. Now, how can I find what my asymptotes would be? The really good thing is that asymptotes aren't affected by a vertical translation. So normally my asymptotes would be at pi on 2, 3 pi on 2, 5 pi on 2, and so on. In this case, because I've divided everything by 2, I just need to divide all of these by 2. So that would be pi on 4, 3 pi on 4, 5 pi on 4, and so on. So that's how I would find out all of these equations here. So that would be pi on 4, 3 pi on 4, 5 pi on 4. The next one would be 7 pi on 4, which is less than 2 pi. So I can still have that. And then what would happen, so that I can get to that 8 pi on 4, I would actually just need a tiny little bit to end there. And what you'll notice is that where it's going to end is the same as where it starts, again, because it's that 2 pi cycle. So at 2 pi, my y value will be root 3. So I know I said no more sketching, but it does help to sort of visualize exactly what it is that you're drawing, and also to see a tan graph with a translation. That was a big exercise, but you have now completed sketching tan graphs.